And our next speaker will be Xavier Siemens, whose title is there, Results from the NANOGrav Search for Nanohertz Gravitational Waves and Cosmic Strings and Other Sources. I guess there's been a slight change in the title.
Yeah, sorry about that. It's a pleasure and an honor to be here. Thank you for the invitation. So I'm going to tell you about our latest results, our latest published results. And NANOGrav is the North American Nanohertz Observatory for Gravitational Waves. There's about 200 of us in the US and Canada. We collaborate with partners in Europe, Australia, India, China, and South Africa to form the International Pulsar Timing Array. We were fortunate in 2015 to become a Physics Frontier Center in the US, and we just renewed our support actually this past April for another few years. So we're part of a suite of experiments that are exploring the spectrum of gravitational waves. You've all heard of LIGO, of course, at the highest frequencies. LIGO is sensitive to binary black hole systems with masses between a few tens of solar masses. We operate at a few nanohertz and 11 orders of magnitude away in frequency. So our black holes are our black hole binaries are billions of solar masses. And we're also sensitive to sources of primordial gravitational waves, which I'll discuss toward the end of this presentation. Our bread and butter source is supermassive binary black holes, as I mentioned. We know that supermassive black holes exist at the cores of galaxies. We also think that galaxies evolve through mergers, meaning early in the universe, smaller galaxies merge together to form slightly larger galaxies, and so on. And this hierarchical set of mergers that results in the size and structure of galaxies that we observe around us today. When these galaxies merge, the supermassive black holes at their centers will also merge, producing a variety of signals. The loudest one, the one that we expect to detect first, is the stochastic background, which is a red noise process, which is the superposition of all of the gravitational waves produced by all the supermassive black holes that are merging in the universe. But we are building a gravitational wave detector, and there are other sources at these frequencies, which include cosmic strings, inflation, and phase transitions in the early universe. So let me talk a little bit about our detector, how our detector works. The first component is our pulsars, which are a kind of neutron star. They have strong magnetic fields, and they emit radiation beams, radio beams out of their magnetic poles. And if the rotational axis and the magnetic axes are not aligned, then they sweep in space like the beacon on a lighthouse. And so if we observe them as point sources of radio bursts, basically, they're basically like clocks that are spread out throughout the galaxy. So that's the first component. The second component are our radio telescopes. We are fortunate to have access to some of the most sensitive radio telescopes in the world. Up until December of this past December, we were using Arecibo. You probably heard that unfortunately that telescope collapsed. We still have about 15 years of data from that radio telescope, which we will continue to use and will anchor future data sets. We also use the Green Bank telescope. This is a 100-meter dish, and we use the Very Large Array and the Canadian H1 mapping experiment telescope. So how does our experiment work? What we do is we keep track of every rotation that a pulsar is doing over many years. We construct something called a timing model, and I'll refer to this later when I discuss the results. And that timing model predicts when a particular pulse from a pulsar will arrive at our radio telescope. So what are the pieces of this timing model? Well, the pulsar is somewhere in the sky, and the Earth moves around the sun once a year. So when the Earth is moving toward the pulsar, the pulses will arrive a little bit earlier. When it's moving away, they'll arrive a little bit later. So the sky location, for example, is one of those parameters in our timing model. The pulsar could be in a binary system. We model that entire binary system as well as say the pulsar is orbiting around its companion. Then when the pulses arrive depends on the state of that orbit. So all those things, the so-called deterministic part of the time of arrival of a particular pulse from a pulsar goes into a timing model. But we don't get it quite right. We have differences when we go and then measure the times of arrival. We have differences between the model time and the actual time. This is called the timing residual. And the gravitational waves will change the time of arrival of pulses. If you imagine you have an array of such pulsars spread out through the galaxy and a gravitational wave passing through the galaxy and stretching it and squeezing it, that will change the time at which these pulses arrive. So we look for gravitational waves in this timing residual data. What allows us to do this experiment and do this experiment so well is that the pulsars that we use are just outstandingly accurate. We can predict the time of arrival of pulses from our best pulsars to a few tens of nanoseconds. So over a time scale of 15 years, we can say, oh, next year, this particular pulse will arrive at this time, plus or minus, say, 30 nanoseconds. That precision is what allows us to do this experiment. It's not enough to have one pulsar, even though these are even though pulsars, some subset of pulsars, millisecond pulsars are amazing clocks. There's still complicated astrophysics that needs to be modeled and understood. And really what we're looking for is a correlated signal in our data, not just what we could see in a single pulsar, because we wouldn't know whether that's a gravitational wave, but rather a correlated signal from all of our pulsars. As an example, if you have a stochastic background of gravitational waves, then the gravitational wave perturbations are going to be correlated among different pulsars according to this plot down here called the Hellings and Downs curve. And what this shows is if you have two pulsars with an angular separation as given on the x-axis, then the arrival time deviations from the pulses will be correlated, most correlated when they are at zero angular separation, anti-correlated at around 80 degrees or so, in this sort of quasi-quadrupolar shape that you see here. So we have, in NANOGrav, we have produced several data releases, the 5-year data release, a 9-year, 11-year, the 12.5-year, that's the data release that I will be discussing the results of during this talk. And each time what we've done is we've increased the number of pulsars that we time. That's really key to our sensitivity, is having as many pulsars as possible. And we've also been improving the instrumentation to improve the accuracy that we can make the measurements of these times of arrival of the pulses. And we're working right now on putting together a follow-up data set, the 15-year, which I will also discuss briefly. The plot on the right here shows each of these dots. The color represents the radio frequency. We make measurements at different radio frequencies with our radio telescopes. And each of these points is an epoch at which we took an observation. And this just shows the enormous increase, starting with our 5-year data set a few years ago, in the enormous increase in the number of pulsars that we time, and also just in the sheer number of data points that we have taken over the years. This 12.5-year result got a lot of press. Here's an example and I will tell you what this result means. Before I do that, I want to, in case you're not familiar with this, I'm going to be talking about white noise and red noise, and I just want to clarify what that is right away. So if you plot the power spectrum of a noise process versus frequency, red noise processes are processes that have more power at low frequencies than at high frequencies, so they'll have a spectrum. This is really a log of the power spectrum versus log frequency. So they'll have more power at low frequencies than at high frequencies. And then there's also white noise processes, which have the same power at all frequencies. In our data, we have several kinds of red noises and several kinds of white noises that we add in. You might have also heard of blue noise. We don't have that. That's not a noise type that shows up in our data. So before I discuss the results, let me tell you a little bit about the model that we use. So each of our pulsars has a timing model, and I described this earlier when I was talking about the sky location the binary parameters of the pulsar frequency, a spin down, all those sort of non-gravitational wave deterministic pieces are in the timing model, and each pulsar has one of those. The pulsars also have several kinds of white noise and also some red noise as well, intrinsic to each pulsar. So we have, in the case of the 12.5-year data set, we have 45 pulsars. So n is 45 here. So we have 45 of these boxes. And in addition, we add a common signal, which is a signal which is common across pulsars and it's possibly correlated. And the gravitational wave stochastic background, no matter the source, will first show up in our data as a common red noise process, a red noise process that has the same amplitude and spectral index across all of our pulsars. And in due course, we will build up enough significance that we should detect correlations that this is indeed due to a gravitational wave. So here are those boxes again. So that we as I mentioned, we model this red noise piece as a power law. So it's just A times F to the minus gamma. So each pulsar has its own amplitude and its own spectral index for the red noise, and that's important. And then in addition to that, we add a common signal. So a signal that has the same amplitude and the same spectral index across all pulsars. And these quantities, A sub CP and gamma sub CP, that's what was in the plots in our 12.5-year paper. If you saw it, this is the quantity of interest. This is and we made a strong detection of a process with a common amplitude and spectral index across pulsars. You can see it here in a couple of different forms. Just ignore the green traces here in both of these plots. The blue and the orange are two similar ways of calculating what the amplitude and the spectral index are. And you can see we get very nice closed contours. And this is dominated by the lowest two frequency bins in our data, which is shown on the left. So how do we actually measure the significance with which we detect various things like a common process or maybe correlations? What we do is we use a Bayes factor to compare different models. And these Bayes factors tell us how much more or less likely one model is compared to another model. So the first model down here is a pulsar called pulsar intrinsic noise only. So what's that? That's this model. That's the model where you only have these boxes here. So each pulsar just has its own set of noises, and that's all that goes into the model. So that's this box over here. The next model that we compare that to is a model with a common amplitude. All right, so that is this model here. It's these boxes up here plus this common signal boxes down there. And we compare those two models. And what we find is a Bayes factor of several hundred to a few tens of thousands, depending on the details of what we do. So this is a strong detection of a common red noise process in our data. And the next question we want to ask is this common process correlated? And there are different kinds of correlations. The middle box here, HD, that stands for Hellings and Downs. That's that quadrupolar correlation that I showed earlier. There are other kinds of correlations that we could have in our data coming from, for example, some systematics. A monopole would come from a clock systematic. A dipole would come from a solar system ephemerity systematic. And when we compare a model that has that red noise, which is correlated, versus that same red noise, but without the correlations, we see a Bayes factor of about 2 to 4. That means that there's 2 to 1 to 4 to 1 odds of the noise process being there. This is nothing to write home about. What is interesting is that these other systematic types of correlations that we considered are disfavored. So this one is, I would say, not particularly favored nor disfavored. The monopole and dipole correlations of this red noise process are disfavored. So here's another way of seeing that that the Bayes factor of 2 to 4 is nothing to write home about. These are the correlations as a function of angular separation in our 11-year data set and our 12-year data set. Yeah, you could think that there's something here, that fits the blue Hellings-Downs curve, but you can also fit a straight line here, which is shown in the monopole in the orange here, pretty well as well to this data. So that sort of tells you that we're not really seeing any kind of strong evidence of correlations. Another thing you can do is to figure out what are the chances that noise alone will give you a Bayes factor of 2 to 4. And we do that in a couple of different ways. We do phase shifts in our data, which is very similar. If you're familiar with LIGO, they time shift their data. They do time slides of their data, and this is a very similar thing. We do phase shifts on our data that breaks the correlations. Another thing you can do is change the sky location of the pulsars, but not tell our code that you've done that. And so you're basically breaking all the correlations, the Hellings-Downs correlations. Both of those give you very similar results, with the chances of noise alone giving you this Bayes factor of about 10%. So yeah, you're somewhat out in the tail here of the distribution, but 10% of the time, in the absence of correlations, will still give you a Bayes factor of 2 to 4. So where does that leave us? Well, we are definitely detecting a common red noise process, but that means that it has the same amplitude and spectral index across pulsars, but we don't yet know what this is. It doesn't have significant quadrupolar correlations, which will be the telltale sign of gravitational waves, but curiously, it does favor monopolar and dipolar correlations that would come from some known systematics that we could have in our data. So we're following this result up in our 15-year data set, and we're collaborating with our international colleagues who have their own independent data sets. So stay tuned for results. We are currently doing this, and we expect to have results, I would say, on the timescale of about a year or so from now. All right, so let me talk a little bit about cosmological sources of gravitational waves, which are of most interest to you all. I think so. We do expect the most promising source are supermassive binary black holes, and we do expect to make a detection if the astrophysics, if we understand the astrophysics well, which we think we do, quite soon. We may be seeing the first hints of it right now. We're just not sure. And this will be followed by the detection of individual binaries that stick up above the background. So what about cosmic strings, inflation, phase transitions? There's a couple of questions. How can we distinguish between different types of sources? Suppose we detect a background. How do we know that it's supermassive black holes and not cosmic strings, for example, or some other source? And if there's more than one stochastic background in our data, how do we distinguish between, how can we measure that? So I'll try to talk about this a little bit in the next few minutes. These sources are speculative, but they're very important, because a positive detection would have profound consequences. So as you know, cosmic strings can form in phase transitions in the early universe. Cosmic superstrings are fundamental strings that are stretched to macroscopic scales by the expansion of the universe. And in the simplest models of superstrings, they behave very much like the cosmic strings of field theory. They're characterized by a mass per unit length mu, which is usually expressed in terms of the Newton's constant times mu, which is dimensionless. So for example, gut strings have a value of g mu of 10 to the minus 6. And pulsar timing arrays are actually currently the most sensitive experiment to cosmic strings, and they give the best constraints. This is the constraint that we got up until before the time that we detected this common red noise process. And note that this is several orders of magnitude below the gut scale, which is really quite nice. So this is a plot from a paper that Ken Olam and Jose Blanco Villado and I wrote a few years ago, with the best upper limits coming from pulsar timing arrays. This shows omega, the spectrum, omega versus frequency for this is the pulsar timing array limit here shown in this wedge, and I show here the background due to supermassive binary black holes and the slope of this line here, basically. So what I was trying to show here is that these two the two slopes in omega of supermassive binary black holes and cosmic strings are at this frequency quite similar, and they may be quite hard to tell apart. That was several years ago. In the meantime, we have detected this common red noise process that we don't know what it is. There were a lot of papers about cosmic strings on the archive that are citing this. I believe, I hope that this is the latest one that I'm aware of. And I think there's the interpretation of what kind of cosmic strings you're seeing depends on the particular model of how cosmic strings evolve and the emission model that you use. But I believe that the results were more or less the same. Maybe someone in the audience can correct me if I'm wrong.
5 minutes.
Yeah, understood. Yeah, I'm almost done. So this is what I have on the y-axis is the log of the amplitude versus the spectral index. This is taken from this paper down here. What is shown here is for different emission models. So mono is a monochromatic emission just associated with the size of the cosmic string loop that's producing a gravitational wave, kink emission, cusp emission, and all of these emission models essentially give, they're very robust. They give more or less the same result. They're in about the same area. And the contours here show the NANOGrav common red noise process. So what you see here is that the common red noise is, if this is produced by cosmic strings, then they would be produced by cosmic strings at with a G mu of a few times 10 to the minus 11. And this is a little bit higher than our upper limit that we had earlier, and I'll be happy to talk about that if someone has that question later. In the case of cosmic superstrings, you have reconnection probabilities that are less than or equal to 1, and there's a couple of reasons for that. One of them is that strings interact probabilistically with a probability proportional to the square of the string coupling, and also that these models have extra dimensions, and even though strings will meet in 3 dimensions, they'll actually miss each other in the extra dimensions. Though both of those effects have reduced the reconnection probability for cosmic superstrings. And here you see the effect of the reconnection probability, again, in a plot taken from this paper. If you reduce the reconnection probability, what that does effectively is to raise the density of strings in the network. Low values of the reconnection probability are disfavored by the data. I would say, before you read too much into this, I would say, we're analyzing more data. These contours are very broad. And so we'll eventually these contours will settle into something that we really believe. At the moment, I wouldn't overinterpret this, the data. Let me put it that way. Let me talk a little bit about phase transitions in the last few minutes. So the horizon at the QCD phase transition time is about 10 kilometers, and this is stretched by the expansion of the universe to about a parsec or 3 light years. And this is about the wavelength of gravitational wave sensitivity. This was actually pointed out by Ed Whitten back in the 80s, the first person to my knowledge to point this out. And of course, if there's any kind of process, that interesting physics that is going on at the QCD phase transition time that generates gravitational waves, then the gravitational waves get stretched into the PTA band today. So as far as we know, the QCD phase transition is not a first order phase transition, it's just a crossover, but there are beyond the standard model situations which can lead to first order phase transitions and other interesting physics where you could in fact produce a background due to bubble collisions and other things like that. So to summarize, we expect the detection of a stochastic background from supermassive binding black holes in the next few years. I haven't mentioned inflation actually, so let me say a little bit about that now. This red noise process that we're detecting, if it is due to gravitational waves, is certainly not from vanilla inflation because the amplitude is too large. That's already ruled out by cosmic microwave background experiments. There are modifications to inflation where you can have a blue spectrum and omega, so you can have, satisfy the constraint that comes from the CMB and then have a rise that might, but vanilla inflation is certainly not what we're seeing. For cosmic strings, the PTAs are the most sensitive experiment, and we've already ruled out a chunk of the parameter space. However, when it comes to distinguishing the two, this may be complicated because the spectral index looks like it's similar-ish to what you get from supermassive binary black holes. However, that really depends on where you end up on the omega versus frequency part of the spectrum. But if you end up where I showed earlier on the plot, it may be hard to distinguish. However, distinguishing the two is not just about the spectral index. There are other things like anisotropies that we could use. The background from strings is expected to be very isotropic, whereas the supermassive binary black hole background is not. So any deviations from isotropy would be a very good telltale sign. And of course, LISA in 2034 will settle any lingering doubts. However, I think we can resolve this before then. And I also mentioned phase transitions, and there's potentially the same problem depending on where you end up on the spectrum of the produced by phase transitions. So I will leave up my last slide, and I am out of time, so I will stop there. Thank you.
Okay, thank you for a talk with some tantalizing results and questions, anyone? Let me see, I see Eva.
Thanks for the really interesting talk. When it comes to the supermassive black holes, would your results be able to help with questions about how they formed, how rapidly they were able to form, and that sort of thing, which I gather are sort of persistent puzzles in astrophysics?
So that's a great question. So the pieces that come into the predictions of the background are the galaxy merger rates, the masses of black holes that live in a certain mass galaxy, which does tie into what you were asking directly, I think. And also what the environments are like at the cores of galaxies. So those are the three main ingredients that I had a few slides about this, but I actually took them out of this presentation. Those are the three main ingredients that enter the calculation of the background. So once we measure the spectrum, we can solve the inverse problem, and we can turn it around and say, okay, well, this must be the galaxy merger rate. This must be what the environments at the centers of galaxies is like, at the cores of galaxies is like that black holes live in. And this must be the masses of black holes that live in a certain mass galaxy. This is called the M sigma relation. So to the degree that the M sigma relation will shed light on your question, getting to the bottom of the M sigma relation or MM bulge relation, we'll answer the question that you asked. We will be able to shed light on this. I think what you were asking though is, how do we get such massive black holes so quickly in the universe? I don't know how much we'll be able to say about that particular question, other than whatever light we may shed on the M sigma or MM bulge relation.
Okay, looks like Sandip Trivedi next.
Hi. Yeah. No, thanks for a very interesting talk. I had a sort of similar question to Eva's, but just more simply, how massive would the supermassive black holes have to be to account for your red signal you might be seeing? Just ballpark.
Billion solar masses.
Billion solar masses.
Yeah. At least those are the black holes in the standard model that we use to produce our sort of nominal spectra for these black holes live at the centers of galaxies, and they're order billion solar mass.
So like order of magnitude like M87, if I'm right? Or is that off?
Exactly. Yes.
Okay.
Yeah.
Very exciting. Thanks.
Okay, maybe one from the chat. Sethi asked, can you comment more on observing the gravitational memory effect from PTAs?
Yeah. So all of these are really great questions. So the memory effect is very generic to any system that produces gravitational waves. Generally, there will be some memory that accompanies it. And that's where, for us, so my graduate student here at OSU is actually working on this. One of our flagship searches is for black hole, for for memory type searches. And my graduate student is actually working on this. And so the merger rate of supermassive black holes is sufficiently low at our strains, at the strains that we are sensitive to, something like 10 to the minus 15, 10 to the minus 16, that we may detect one every 10 or 100 years or something like that. So we're not, at least, we understand the physics correctly. The astrophysics is right. The expectations for the rate of these bursts from supermassive black holes is quite low. We could get lucky, of course, but the rate is expected to be low. But like I mentioned earlier, the memory is very generic. There's all kinds of systems that emit memory that have a memory signal associated with them, and this is really why we search for them, because of the unknown unknowns. So that's as much as I think I can comment on this question. It's a really nice question.
Okay, and then I'll defer to the organizers here. Should we allow one more question, or do we need to move on?
I would say you can have one more question.
Okay, let's have Xiaogang.
Yeah, here you mentioned there's a cosmic string in early universe. I wonder whether there's any constraint on the energy scale of a cosmic string from this astrophysics observation.
Yeah, I mean the energy scale is that's another great question. The energy scale is basically given by G mu, right? So
yeah.
G mu 10 to the minus 6. So you're basically, so that's the gut scale basically, and the results indicate a G mu of a few times 10 to the minus 11. So it is 2.5 orders of magnitude below the gut scale.
So what that means? That means the cosmic string beyond this scale is ruled out, or something. I try to understand the meaning of this graph.
Right. Yeah. That's right. That's correct. I mean, if the only signal that we're detecting right now, this common red noise process, is centered here. There's nothing up here. There's nothing down there. So G mu of 10 to the minus 9 is not allowed. So right now, if the signal is due to cosmic strings, then the cosmic strings that would produce it, that are allowed to produce it, are something like a few times 10 to the minus 11, maybe 10 to the minus 10, something like that. 2 to 3 orders of magnitude, 2 to 2.5 orders of magnitude below the gut scale.
Okay, thank you very much.
Okay, so I presume we should wrap up. I'll just mention, though, there are a couple of questions in the chat that you may want to look at, but I'll go ahead and end the session there. So thank you again for a very interesting talk.
Thank you.
Thank you. Thanks, Steve. So welcome, everyone. Hope you are having an uneventful morning, afternoon, or evening, and a relaxed one. And we go to our last